Okay. Do you see my screen still again, presenter? Great, thank you. Okay, well, 2 minutes past the hour, so let's get going. Um, Thank you so much for joining, which is the USV webinar. Some of you would have probably joined before, and this is a webinar series that's organized by OASIS, Observing Air Sea Interaction Strategy group. And we have these webinar series every few months. They haven't been as regular as we hope, like every month or every 2 months, but they do come and go. And we have also our old webinar series available for you to go and check out the previous talks. And if you see this link here on the screen, I'm going to put these in the chat just now, so you don't need to try and scribble them down here. I'm going to put a series of links later that can help you to go and register here if you're not registered at these USV webinar series. We are very fortunate to have two guests today, Beth Siddle and Liz McGeorge. I'm going to come back to introducing them. But the format is two short presentations from them, and then we'll open it up for questions and discussion. I thought we'll take the opportunity while we have the community together here to show a few little things. One little highlight was that today we got some new USVs in the water this morning, deployed off the coast of South Africa. So Johan and Marcel have been helping piloting these sail buoys, which is quite fun. So these are doing transects inshore, offshore of the Agulhas Current, together with some of the colleagues in South Africa at SAON and Sea Technology Services, and in the Department of Science and Technology. So this is great, and these sail buoys provide some cool data of ocean currents from the ADCPs and the heat fluxes associated with the atmospheric and ocean sensors that they house. If anyone knows of Southern African or African colleagues that are not far from Cape Town, then in March we're running a USV workshop that's really about exposing the value of USVs for research, monitoring, resource management around the coast, with an application towards Southern Africa. And applications are closing on the 19th of February. And I'll put the link in the chat as well. So if you know anyone who doesn't know about this yet, who may be interested, then please do let them know about this opportunity. Then we're always seeking new and excited people to join the USV network, particularly in a more active manner, so helping us push the network forward. So, that might be coming in and helping us with these USV webinar series and other aspects of the network. If you're interested to join us and play a more stronger role or more active role, then please do get hold of us, either through Ruth Patterson, myself, or Megan. Then otherwise, also please let us know if you have any lightning talk that you would like to provide us in a future webinar. You would be most welcome. And then these other last links here are resources to finding out how to get involved in OASIS, or in particular the USV webinar series and the other webinars that are available, such as the Observing Air Sea Fluxes from Space webinar that happens. There's also the links to allow you to sign up and get the right links for Zoom and access to those webinars. Okay, so then I take us back to today, and we're going to start off with this presentation by Beth Siddle using the AutoNaut and showing how the AutoNaut can be a great means to observe air sea fluxes and also carry things like gliders, which is very exciting. Beth is a almost finished PhD student at the University of East Anglia. So apparently she tells me she's submitting like next week. So she's very brave and crazy to give us this extra presentation in a really busy schedule. So thanks so much, Beth. And we'll follow that by Liz McGeorge, who's originally from New Zealand, but now a postdoc at NOAA-PMEL and University of Washington, closely associated with Megan and Yolanda Sarah. who's also going to show us another type of USV, Saildrone, also doing work around ocean processes and air-sea interactions. So we're going to start with those two presentations. We can take one or two brief questions at the end of Beth's talk, and then at the end of Liz's talk, and open it up directly from there into discussion and further questions. And if that sounds all good to you, then I would like to ask Beth to start sharing her screen, and she could start presenting.
Yeah.
I need to stop sharing mine if I can find my Zoom window. There we go.
There we go. Okay. Hopefully you can all see that okay.
That looks great.
Great, thank you. So I'm going to be talking a little about our deployment experience and our experience calculating air-sea heat fluxes and ocean heat budgets with Caravela, which is an AutoNaut USV owned by the University of East Anglia. And this project is kind of the brainchild of Karen Hayward and Ben Webber and myself. So some cool photos to start. A lot of this talk is going to focus on what was going on the left photo, which is a photograph of Caravela deployed in the northwestern tropical Atlantic back in 2020. I had hoped to talk a little bit about the photo on the right, which was our most recent deployment of Caravela, and that was on the edge of the Weddell Sea down in the Antarctic early last year. I think it was February 2024, January or February. But unfortunately, we've not had anybody able to go through and do the air sea flux calculations from that deployment yet. So I thought I'd just throw in a photo for now, and we can always come back to that in the future. So a little bit about what Caravela is. Caravela is an uncrewed surface vessel, designed and built by the company AutoNaut, which is based over here in the UK. Caravela is a little bit different. It is a unique vessel in that the design has been changed so that she can carry a sea glider, which is a totally separate, autonomous underwater profiler, this yellow bit under here. And that is able to carry out ocean profiles down to 1,000 meters deep to give us some really interesting complementary ocean information to go with these air-sea interaction studies that we're doing at the surface with this vessel. To give you a little bit of info on what Caravela can measure, in terms of the meteorology, we've got humidity, air temperature, wind velocity, and then we also have downwelling, long wave, and short wave radiation, which is pretty cool. And then we have an ADCP and a CTD. The CTD has changed from what's on this diagram here. It is now a pumped CTD to help get around issues of conductivity spiking when we've got the vessel motion, things like that. So hopefully this works. I've got a little video. Please do tell me if this doesn't show up for you guys. But this is a deployment of, oh, I think, interrupt if you can't hear me anymore, please. But this is a deployment of Caravela of the coast of the UK, where we're just kind of looking at testing. And what I was hoping to show you was the release of the sea glider, which is actually included in this footage. But it looks like my internet connection isn't going to be quite good enough to facilitate that because I have just lost the call to some degree. Can you guys follow me okay now? Am I back? Yeah.
We hear you fine, but the video is just a bit staggered, not really moving.
Yeah, that's fine. We'll skip the video. I can, if anyone's interested in seeing that, I can distribute that another time. Sorry about that. That's a bit of a shame. So what I'll talk about instead is we'll jump straight into what we did with the Eureka campaign. So this was a campaign back in 2020 off the coast of Barbados. And the campaign was this massive international campaign, had loads of collaborators and was looking at the interplay between clouds, convection, and circulation, and their role in climate change. So really trying to look at cloud microphysics and use that to kind of enhance climate models and all sorts of things related to that. This project had 4 ships, 4 planes all out at the same time. So it was a massive project, really cool. and ended up spanning all sorts of things: oceanography, meteorology, atmospheric chemistry. There was a lot going on. So I encourage you to check it out if you haven't come across that project before. Um, so the um, sorry, there we go. So what we did within the project was we were interested in going out and doing some air-sea interaction studies, which we did by setting up Caravela on Barbados, piloted her out to the study site at the top right of our map here. And on the way, we released our sea glider, which then later joined us to do some complementary studies of the area. And we also had a couple of sea gliders that were deployed from a ship into our study site region. What we were also interested in doing within this campaign was not only looking at whether or not we could calculate the air sea fluxes from our observations and do an observational mixed layer heat budget, but we were interested in looking at kind of validating ERA 5 in the region and seeing if we could identify any biases. So I'll jump straight into showing you some results. And these are the time series of the various fluxes calculated from this campaign. So we have the shortwave radiated flux, long-wave radiated flux, sensible and latent heat fluxes, and then we add those all together to get our net heat flux in the top panel. The grey lines on these are the 4 ERA 5 grid points that surround our study site. The black line is what we use for our comparison. That's the mean of those 4 grid points. And then our red line is our fluxes derived from our observations. And just to caveat, we did have to substitute in ERA 5 winds for these because we had some issues with the wind data that we'd collected from Caravela in this instance. That has all now been resolved as far as we know. So future deployments will have their observed winds in there. And we did this using the Python version of Core 3.5. So we've got the shortwave fluxes, and you can see there are days where ERA 5 is slightly underestimating the fluxes and days where ERA 5 is overestimating our fluxes much more significantly. With our long wave fluxes, I will caveat this with, unfortunately, this looks like to be, this offset between the two looks like it's down to a sampling issue with the sensor that we had on Caravela. And we never quite got down to the bottom of why we have such an offset in the observations. But what we've had to do for the kind of taking these calculations forward is just kind of discard that observed data and use ERA 5 long wave to substitute in. Our sensible heat fluxes, you can see there is an offset between Caravela and ERA 5, and the same with the latent heat fluxes. And now the latent heat flux is quite significant. So the shortwave fluxes and the latent fluxes are the main contributors to the net heat flux here. And so they really play into the offsets. What happens if we take the shortwave radiated flux, sensible flux, and latent heat fluxes from our observations and use that long wave radiated flux from ERA 5, where we've got the problems with the observations? We actually find that that combination as a net heat flux is ERA 5 is for a daily average, ERA 5 is overestimating the heat loss to the atmosphere by about 30 watts per square meter compared to that kind of observational combination. So quite a significant difference when we look at ERA 5 alone. And so we were like, well, what potentially could be going on that's causing these things to not quite line up? So we went in and had a look at the time series of some of the individual bulk observations that would have contributed to these fluxes. We can see in the ERA 5 SSTs, there's days where there's quite significant decreases in the temperatures that we get from ERA 5, which aren't mapping to what we see in the observations in these from the 10th to the 14th of February in the middle here. Consistently, ERA 5 is giving us lower air temperatures than what we're getting from the observations by Caravela, which will be playing quite significantly into those discrepancies in the fluxes. Now, we couldn't get relative humidity directly from ERA 5 at the point that we did this, so we took dew point temperature and kind of calculated this back to find out what it would have been, and find that on average, ERA 5 is giving a relative humidity 3.4% lower than what we get in observations. So again, this is a number that will be playing into seeing these discrepancies in our fluxes. So we've identified some places that Era 5 is not quite getting this stuff right, and that will be playing into regional biases. So we've found something really cool. We've found a way that we can potentially go off and improve fluxes for this region and improve that budget closure. So I'm starting to bring up budget a little bit. So we'll move on to the ocean heat budget. So for those ocean heat budgets, for those who haven't encountered them before, is where you kind of take the temperature evolution of the ocean mixed layer, which is this kind of turbulent, well-mixed layer at the surface, and you look at all the processes that could be bringing heat in and out of that. The air-sea fluxes, horizontal processes, vertical processes. Some examples are horizontal advection and entrainment, and those are the ones that we've focused on within the scope of our work. Now, what we had a look at doing was using the observations from the sea gliders to give us a mixed layer average temperature so that we could go off and look at the temperature tendency and have a go at closing the heat budget. Now, the slide I'm going to show you just neglects every other process except for the contribution from the air-sea heat fluxes, and I'll explain in a minute why we've done that. There's a whole thesis chapter basically dedicated to trying to look at the other terms. So bear with me and I'll come on to talking about that a little bit more. Um, don't worry too much about all the information that's here. That's for those of you who are really, really interested in your heat budgets. You can have a look at the lines as I'm talking. But for those of you less so, the thing I want to draw attention to is this brown line in this top plot is our net heat flux estimate Q0 from our observations. We use including the QPen correction, which is the correction for radiation lost at the that passes through the bottom of the mixed layer, which is particularly important in clear waters like those in this region. In our second panel, we have this mixed layer average temperature that we've got from the sea gliders. And what we're doing is we're trying to work out if these processes from the surface match up to the temperature change that we see from here. So we look at that with the temperature tendency and the net heat flux term down in this fourth panel, panel D here, using this equation at the top right. And what we actually see is we get a pretty good closure of the mixed layer heat budget. The I've got the number written down. The root mean square difference between these, if we do a 6-hour rolling average, is 0.008 degrees C per hour. So it's a pretty good closure. This is really encouraging. There's going to be uncertainties in this based on our sampling. There's going to be errors. But that's a nice budget closure. We're pretty well explaining how the heat is moving around just by looking at the net air-sea heat fluxes. And that's not necessarily unexpected because those are known to be the dominant drivers of heat budget in the changes in this region. Now, I talked about ignoring the other terms of the heat budget, and that is we have calculated the horizontal advection and we have calculated the entrainment. I don't show the numbers in this talk, and that is because they actually significantly worsen the closure of the heat budget. So I think if we look at this cumulatively over the whole 9 days that we're in the study site, we have a 19 watt per square meter residual, just looking at the net heat flux. If we include the horizontal advection and the entrainment that we've calculated, this goes from a positive residual of 19 watts per square meter to like a negative of 56. So it's significantly throwing off the budget. And that is all down to sampling strategy. So we set out to do this campaign looking at sub-mesoscale features. And we kind of changed the target of this campaign as it went on. So we have this bow tie pattern that was going on within our study site, and that was intended to capture these sub-mesoscale features so we could go around and study them. What we've ended up is doing this big heat budget. When you've got a big heat budget like this, where you're looking at all these significant terms like the horizontal advection and the horizontal component of the entrainment, you need good coverage across your study site, like in this panel A. So where we've got Caravela is our red dot, and our two sea gliders are green and blue. And we've got this really nice right angle triangle, so we've got good coverage. We can calculate temperature gradients from that and get an idea of what's going on. And we get good values, like reliable values to feed into to horizontal advection, the heat budget doing that. What we find quite often as the platforms were moving around the study site is we'd actually end up with them forming a line or forming a very, very tiny triangle and being really close together in either the lat and long space. And what we've ended up doing is having to set up this whole QC process where we try and filter out all of these different platform orientation conditions because they massively throw off the temperature gradients and our ability to calculate these other terms in the heat budget. So that's really interesting, but that would be a whole nother talk in itself. So all I'm bringing into it, kind of bringing to this talk today is like, this was really significant in our campaign. And so mission planning is really important for how you want to go about kind of tackling these kind of questions in the future. And please, learn from our mistakes and don't end up with your vessels close together if you're looking at doing a heat budget like this from observations. So I'll just wrap up kind of this brief overview. Bulk fluxes from our Caravela USV observations did help to quantify the regional biases in ERA 5, and we found some really interesting stuff there. If we use our best heat flux estimate, where we sub in those observed long wave fluxes with ERA 5 because of that issue, we can identify a 30 watt per meter square, 30 watts per meter squared offset in ERA 5 to the observations, which is a significant amount and does play into not being able to close heat budgets and fully represent air-sea heat fluxes in the way that this community wants to. And mission design can significantly restrict your ability to calculate the other important terms in your heat budget. So really make sure you're looking at your kind of vessel separation if you're interested in observationally calculating horizontal advection and other horizontal processes. I hope that was interesting. Hope that wasn't too fast. And I will leave it there.
Fantastic. Thank you, Beth. That was great. Really wonderful to see this AutoNaut, which we haven't had featured so many times before in the webinar series. This is great. Thank you. Let's take some quick questions before we go to Liz. If you want to have a question, please put your hand up or unmute yourself and show your face and ask your question to Beth. Yolanda.
Yeah, thank you. Very nice talk. I wondered about so when you showed the SSTs of ERA 5 and how they have some low values, and that would be consistent then, I think, with your air temperature biases. But SST is not a product of ERA 5, right? It's a boundary condition. So I wonder if you'd thought about that and if the had center, I think it's had center SSTs, I'm not sure, but yeah, just wondered.
Yeah, not explicitly. So the way we kind of approached it was taking what was available from the climate data store as what ERA 5 was providing. So yes, you're right. You're right in that it's not necessarily provided by ERA 5, but it's the way we'd looked at it. And I think you're right. Maybe we should have been looking at a different product and rather than taking this boundary condition to kind of better quantify this here. Yeah.
Or maybe it's good news because if they can improve, maybe one of the focuses of improving the fluxes is to improve that product so that the boundary conditions are better for all the reanalyses. I imagine ERA 5 isn't the only one.
Yeah, absolutely. Yeah.
Thank you. It was a very good talk. Thank you.
Thank you.
Any more questions? Johan.
Yes. Hi, Beth. Very nice
Hi.
talk. Super lovely. And congrats on wrapping up the PhD.
Thank
Super
you.
work. I'm quite curious about these platforms and wondering if you did any corrections to the SST regarding any skin corrections. Because we're very much, like I'm using these as well, or it's similar. And you're in the tropics, so you're very much measuring in the warm layer, right?
Yeah. So we didn't explicitly do any skin layer corrections ourselves. We used the version of core that we were using was able to tackle that for us. So yeah, we've not done it explicitly. I've not looked at it explicitly. I just made sure it was accounted for when we did the flux calculations, if that made sense.
Yeah, that's super. Because I think if you input shortwave rate, right, you can do the corrections. But I thought it was if you have sort of bulk or foundation temperature, then that will be accurate. So we might adding some biases or skewing the data maybe.
Yeah, no, it absolutely would be. But yeah, we did in our flux calculations, we have made sure to account for skin.
Yeah, super. Thanks.
That's okay.
Yeah, let's take one more question and then we could move on and take more at the end. Megan.
Yeah. Yeah, very nice. And yeah, really best of luck next week. That's fantastic, wrapping up your thesis work. I'm wondering about the placement of the radiometers on the drone, because this is always so hard, is to find good locations where there's no shadows on the radiometers, and the radiometers don't impact the winds. What's your thoughts on that? Because just based on this little cartoon, it looks like the radiometers might have some shadows on them, and that might impact your solar radiation.
Yeah, it is an issue for sure. So it's not very clear in this diagram, but they are on like a little arm that sticks out to the side. So they have got some distance from the mast. It's just kind of back into the page in this plane.
Okay.
So they're not going to be directly shaded straight down from the mast pole itself, but it is it's still possible as we're moving around. The hope was that the kind of amount of roll that the vessel was experiencing and directional change was that it wouldn't be constantly sat under a shadow. But you're right in that it would be an issue. And the idea is that it is mounted below the wind sensor so that we're hopefully not affecting that wind sensor with anything there.
Right.
But yeah, there's always going to be an issue with these kind of motion corrections on these sensors. And the other thing with this setup is we don't have the separate direct and diffuse radiative components from this. So we can't do that explicit motion correction that's talked about a lot in the literature. So we have to the way we've tackled it is by taking kind of hourly averages to give an idea of what is there and try and get out a lot of those outliers that would have come from shadowing. But yes, much more rigorous motion control would be great if we had the sensor that could give us the information for that.
Yeah, I just wonder, like, if you had two masts instead of one. I don't know.
Yeah, I mean, it would be cool, but that would be one for the manufacturer, not for us, unfortunately.
Yeah, of course. Okay.
Great, thank you. Thanks for the questions so far. We'll come back to more questions for Beth at the end. And therefore, next is Liz, who's going to take us from the tropical Atlantic to the tropical Pacific, I presume, with Saildrone observations.
All right. Cool. Can you guys all see that fine?
Very good.
Great. All right. Thanks, Sib. So yeah, as Sib mentioned, I am working with Megan, who a lot of you probably know, and Yolande Serra, as well as Dong Zhao Zhang at the University of Washington and NOAA-PMEL. So I've been there for a year now, using the Saildrone observations that they've collected in the tropical Pacific throughout the past 7 years. And I've been exploring upper ocean processes and air-sea interactions very broadly. So before I get into what I've actually been working on, I wanted to introduce myself properly. I scrolled through a little bit. There's a bunch of names I don't know. And because it's February 6th, which is a public holiday in New Zealand, it's the anniversary of the signing of the treaty at Waitangi in 1840 between the British Crown and the tribes. I'm going to introduce myself using a pepeha, which is a type of traditional introduction. So, tēnā koutou katoa, no kōtirana me no pōrani o ku tipuna, engari, I tupu ake o ki Ōtautahi Aotearoa, e noho ana o ki Seattle, he postdoctoral scholar ahau I te whare wānanga o Washington, ko tēnei taku mihi ki ngā tangata whenua o te rohe nei, nō reira, tēnā koutou katoa. So this is a traditional greeting, I guess, that we might do. Nothing too outward in there, but I'm from Christchurch, New Zealand, and that is where I did all of my schooling. So I went to the University of Canterbury, first for my Bachelor of Science, and then for my PhD, both in mathematics. So how did I end up here as a postdoc in oceanography? Well, I've always had an interest in the ocean. I've sailed throughout my life, first sailing dinghies as a kid, racing in small boats, and then later sailing on a larger, still small boat relatively. And in 2023, I actually took a year off after my PhD to cross the Pacific with my dad in the boat that you can see at the bottom there, and had the opportunity to observe some very interesting air-sea interactions, sort of live, real time, which was great. So after that year off, I started a postdoc here at UW with Megan and Yolande. And then it's been a year, and today I'm giving a presentation to you all here at OASIS. So I'll start with a little overview of what Saildrone missions PMEL has actually been doing to the tropical Pacific, because I'm not sure if you're all aware of how sort of long they've been going on and how widespread they've been. So they've been doing these missions since 2017. Every year it's been sort of different number of drones, different location of interest, different processes of interest. So over that 7 years, there have been 17 different drones, totaling about 2,500 days. And between the drones, they've done 17,500 kilometers, which is pretty impressive. Those numbers are all with an asterisk. I only calculated them yesterday, and they might be a bit erroneous. And with these drones, every single one has been equipped with the standard surface meteorological sensors, as well as a subsurface downward-looking ADCP. And all of this data is, available on the OCS website, which is great. It's all there to use, but there's a lot of it. So working out how to use it, which bits are of interest, when to use it can be a little bit tricky. So I've been doing a few different projects throughout the past year. My main focus has been trying to better understand how we can use multiple drones sailing in specific patterns to calculate vertical velocities in the upper ocean. And then a second project has been looking at intercomparisons with the TAO array. So as you would have seen on the previous slide, we've sort of been sailing missions that go along those buoy lines in the hopes of passing the moorings, which can then be used as an intercomparison to verify the TAO data. And this has really become important in about the past 2 weeks. I've spent a bit of time on this because there's been a recent article in BAMS. I don't know if you've seen it, but there is potentially some issue with satellite and TAO mismatch in the winds measurements. So we're hoping to use the Saildrones to agree with the article or disagree with the article or say something intelligent about what we think is happening. So essentially since 2020, there's been some change in the moorings, and the satellite products are now about 10% off from what the moorings are reporting. So that's, very interesting. And then I've got a third project that's just starting, which I'll talk more about at the very end if I've got time. But the idea is to enhance accessibility to USD data for research with a specific focus in towards the data I've been using, because it was very intimidating to come in a year ago with sort of no background in this area and to try and get my hands on that data and understand it. So I wanted to make it better and easier for the next postdoc or PhD student that comes in. And yeah, I'll hopefully get some suggestions from the community on ideas for that. All right, so let's zero in on this calculation of vertical velocity from Saildrone ADCP. So I was actually quite fortunate. Beth talked about how the patterns can be quite important for calculating gradients, which is something that I've also grappled with and something that I had thought about discussing today, but then I cut out of my slides. So I'm really glad she brought it up. But what we're trying to do essentially is we get the drones, multiple drones. It could be one drone, but multiple is better, to sail a pattern around a single point. And then once you have data from around that single point, say over a 4-hour period, if the two drones can manage to cover the full perimeter of whatever pattern you're sailing, you've sort of closed the perimeter, and you can calculate a gradient across that shape and that gives you a gradient at the center. And then using the continuity equation, you can get the vertical gradients and velocity, and then integrate and get the vertical velocity itself. So the idea is to use multiple drones sailing around a point to understand, using their ADCP measurements, to understand the vertical velocity at that central location. I've put a lot of work into deciding, what length of time is best for getting that full coverage of the perimeter, and some other factors, other choices as well in this equation. And we've tried to verify it using, models, but it's pretty hard to find high resolution models that can give us a reasonable result for the resolutions we're working on, because this data is all 5 minute. The drones are sailing relatively fast, so they actually, for the most part, do manage to cover the full perimeter in 4 hours. So then to get a model that is sub-daily or even sub-12 hours is kind of hard to find. We have had a chance at that, so I'm quite happy with the results I'm about to show you. There's a few caveats, but I've tried to highlight them. So for 2019, we had 2 drones sailing around 0140 west for 2 weeks. And using the method of calculating these gradients across the box, we get the following results for vertical velocity. So on the top here, I have vertical velocity with depth. And then in the bottom, I've got vertical velocity at 50 meters. So it's just a horizontal cross section at 50 meters, which is the dotted line here in the top plot. And then that's the vertical velocity plot on the bottom. So the red are places where we had the red here in this coloring means there was poor spatial coverage, just like what Beth talked about. So that means the drones ended up clustered on one corner, or they were just sailing really slowly, and so didn't cover the full box. So in places where it's red, the results are potentially erroneous. They're not 100% going to be wrong. There could be a scenario where the particular locations they've sailed still gave us a good gradient, but we can't say anything with confidence about the results in these sort of grey bands. So what was interesting just in making this calculation was we noticed that there is sort of this regular oscillation at quite low amplitude. And then all of a sudden, the amplitude increased a little bit, and we had longer time periods of upwelling. So here and here and sort of here. This is questionable, this final piece. I don't think this is real. So it seems that there's been some sort of change in behavior, and I'm still trying to understand that better. During that same time period at the box, we did have a TIW passing. So that's a tropical instability wave, which is a perturbation in the SST gradients. And I mean, the SST front is quite far to the north, but as the wave propagates westward, the SST front does get a lot closer to where our drones are sailing, which is at this black dot right here. And that's happening in conjunction with the westward expansion of the cold tongue. So throughout the year, the cold tongue expands to the west and brings the SST and the entire region down. And right at this time, we were smack bang in the middle of that extension. So overall, the SST rate was dropping at that location as well. So I want to better understand just what I have calculated as these vertical velocities in the context of what was happening. And then, of course, we've sailed some other boxes. Like, we've done so many missions, there have been other boxes sailed as well. I would like to apply the same methodology to those other boxes sailed, or any other pattern, anything that closes a loop that allows you to calculate a gradient. So it could be like a triangle, or it could be other shapes as well. And then, of course, the end goal is to use this to better plan future missions if we're interested in this upwelling type experiment. So that's kind of like a very stroke of one large brush overview of that project. I've missed a lot of details. So I wanted to talk a little bit more about intercomparisons with the tau array. So this started out looking at ADCPs, because that's obviously what the data I was using for the vertical velocity project, and I wanted to compare to the ADCP that was at 0140 for that same 2019 mission. So I started with that, and that's an ongoing project. We've got a few different ADCP intercomparisons throughout that 7-year period. A few longer than 2 weeks as well, which is great. You have a really longer time series to intercompare. But given the recent paper on this issue with the winds in the past 2 weeks, along with my colleague Nathan Anderson, we've zeroed in on a wind intercomparison. So in that 7-year period, we've got about 26 intercomparisons greater than 2 hours, and 9 different tau moorings are passed. More were passed by, but either the mooring or the Saildrone data was not available. So the tau data sometimes is a little bit spotty, particularly if it's at the end of a deployment. So there were times when we were sailing close to a mooring, but the wind just wasn't available. It's still valuable to be near a mooring because there are other sensors, obviously, that we can compare to, just not the wind. So I had a picture that I was going to show after this slide for the winds, and then I sort of lost confidence, and I was a little bit scared to show it because I feel like I haven't done the due diligence. But I'll summarize what we have sort of found, and that is that for all of the intercomparison periods before 2020, there's about a 10% difference in the mean over that period between tau and Saildrone. And after 2020, there's almost no difference between Saildrone and tau. So what that tells me, bearing in mind I haven't done any height corrections, I haven't done, probably my due diligence on calculating those statistics, is that the new moorings match the Saildrones. So hopefully my Saildrones are good, and that means the new tau moorings are good, which could indicate that there's an issue with how the wind was being processed on the old tau moorings. I'm not going to say any more than that. It seems like a pretty bold claim already. But yeah, that's definitely ongoing work to try and delve into this issue and use the Saildrones in this way, because that's one of the things that's really great about them, is that they're going out there doing these missions, providing data to verify this tau array, which is a super important resource for the community. And we want to be sure that we're confident in what those moorings are reporting back to us. So then my third and final project, which is a new one this year, and I want to thank COS, which is the UW department I'm part of, for funding this, is a project to enhance accessibility to the USV data. And as I mentioned earlier, this is kind of motivated personally by my initial few months working with the Saildrone data, where I was just really struggling. Of course, I was coming in with zero background, so I didn't even know what a NetZDF file was when I started. I've now worked that out, but it would have been nice to work it out a little bit faster. So the goal of this project is to develop some sort of introductory tool. I'm thinking a Python notebook or multiple Python notebooks, where I take a user through reading in some Saildrone data and then looking at a problem of interest. So that could be calculating some ASC fluxes, or maybe even calculating the vertical velocity. That's a fairly simple algorithm. And sort of guiding them through this initial steps. So my first thing is I'm just going to scope potential users, which really means talking to some grad students here at UW. And then I'm going to go ahead and try and develop something and get them to look at it and see how I might improve it. Seb, I was super excited to hear about your workshop. I'm hoping maybe you can share some resources, or you'll have some ideas post-workshop that this worked really well, this didn't work great. Because yeah, I'd like to create a resource that is useful for people interacting with our data, but maybe more as a whole as well, people interacting with any type of sort of weird space-time sampling data that if you've never worked with that, it's quite strange to get your head around what's happening and to know what plots to make and how to look at it. Yeah, so if you have anyone in the community, if you have any specific ideas or suggestions for this project, please feel free to reach out. I'm going to be working on this. So it's 3 months of full-time work for me. So I'm actually going to be working on it over about a 6-month period, the next 6 months. And depending on, how long it takes, I might be able to push it out a little bit longer if I choose to. So yeah, that's kind of my 3 main projects right now, all with USV Saildrone data. So I just wanted to end with a whakatoki or proverb, which I thought would resonate with all of you, and that's he hiringa hangaro he oranga tangata. So innovation and technology for the benefit of all, and I think that is what we're all trying to do here, and that's really admirable. So yeah, any questions or suggestions?
Splendid. Thank you so much, Liz. That's great. A lot of parallel processing going on in your world with these 3 projects and maybe more. Amazing. Fantastic. Thank you so much. Straight away, some questions. Let's just start maybe with 1, 2, or 3 directly for Liz before we open it up to everything we've discussed today. I can start. I was just wondering this vertical velocity estimates from the Saildrones.
Yes.
Do you have any sort of corroborative data coming from hydrographic platforms? Ones that are sampling the upper ocean, maybe gliders or the moorings, that might give you a better context of what the Saildrones are observing compared to what's happening underwater from direct measurements.
Yes. So in 2019, so the mission that I was specifically looking at there with the calculation, it's right near a towel mooring. So we've also got all of the towel line of sensors. So temperature, I think there's a gap in temperature. It's the classic, like we were there and then now there's a gap in that data. But we do have the towel mooring nearby for that one. And then there's another box experiment. There are a few other experiments with other sensors. We just did one recently, this year's mission, where we weren't sailing a box, but we were kind of sandwiching. The applied physics lab had a cruise out and they were using wire walkers, which is a type of drifting mooring with like a prowler on it, I think. I'm not really sure. We sort of found out about it late, but so we were sandwiching those and sailing. So that could be cool to try and calculate some gradients across that and see what the wire walkers are saying is happening in the middle. There's also, we had a glider in the region for that time as well. Katie Coleman, I don't know if she's here, has a glider out in the Pacific right now, and we tried to coordinate with that too. So we definitely, for some of the earlier missions, no. But as we're moving more towards like these later missions, definitely there's been more coordination, I think. Maybe as technology is improving.
Okay, cool. Yeah, thanks. Lev mentioned in the chat if there was any QC done on the USV data in particular. I'm not sure if he means a particular type of QC. Lev, do you want to clarify, or just a general question here?
Yeah, I can jump in. Can y'all hear me okay?
Yeah, we're good.
Yeah.
Yeah, excellent talk. Sorry if I missed if you said any. I was curious after with the Saildrone or the first USV, if there's any QC on the data once it's transferred off the vehicle.
Yes.
Or if it's just kind of assumption that the data is good. Especially, I guess I'm curious with for all data, but also the vertical velocities from the ADCP on the Saildrone, Liz, that you mentioned.
Yeah, so are you talking about how the ADCP like technically reports a W?
Yes, and just also that there's some noise, a lot of noise with that when you're looking at some of the higher resolution. So I'm curious if there's any QC to remove potential bad data.
The answer is yes, there is. So I'm only using the horizontal velocities from the ADCP, not the W. The W is kind of just a weird output that is, it's such a small measurement that it's too erroneous. There definitely was QC on the Saildrone ADCP data, which was done by Dong Zhao and Nathan. I can't comment too much on the process, but it has been QC'd because the original, it's like, I'm not working with the 20 hertz data or anything. I'm working with a 5-minute like subsampled set. So there's definitely been QC. Yeah.
Okay, cool. And we can also just open it up in general, since we're heading up towards the hour. Any other questions for Beth, for Liz, or maybe something else USV related you wanted to pitch in with? Go ahead. I had another question then for Beth. Okay, I'll jump in this one quickly before Lev. The design, the end of your talk with the design experiment, how to do the design issue. You were mentioning that, of course, sometimes the USVs and the gliders all in a line and stuff like that. Have you guys been thinking how you might improve this in the future? And is there ways that you could kind of automate this with sort of AI and get the gliders and the AutoNaut to be more aligned in a triangle or more adjacent to each other?
I mean, I think that would be wonderful if we had something like that. Unfortunately, that's quite far outside of the scope of what our group could do right now. But that would be really cool if we could. And I know there's other groups that work on these kind of AI predictive systems. I think the conclusion we came to was for a study like what we've ended up doing, we should have really gone for some kind of fixed triangle. I think what would have been better would have been 3 gliders in a fixed triangle, which we originally set out to have 3 gliders, but one actually got pulled just at the start of this campaign. So we ended up doing it with 2. And then have Caravela doing the bow tie shape over the top of that triangle. So we then get the sub-mesoscale feature information as well. So that would be how I'd kind of suggest doing it without some nice AI tools. If we could have something that could actively look at what was going on and predict where to go, obviously that would be so much better. But yeah, we'd unfortunately have to look to a different research group for that.
Or the community, yeah.
Yeah.
Yeah. Lev.
I guess I've got a question, 2 questions. First for Beth, and then open is, I guess, Beth, you talked about using the USV to deploy the glider. I was curious if there's any thoughts or looking at about the potential to recover the glider as well, to get into very remote areas, but also to help recharge the glider, since the USV can get solar that the glider cannot. And then I'll ask my second one after, if that's okay.
No, that's okay. So in our specific setup, unfortunately, is deployment only. The glider has to be fitted into that release mechanism on land, so there's no way you can recapture that once in the water. It's very tight, kind of, it needs hands-on work to get it in. So we are deployment only. And then in terms of recharging, there are sea gliders out there that are rechargeable, but unfortunately these sea gliders that I think there are other types of gliders that are rechargeable. The sea gliders that we work with are single-use lithium-ion batteries, so they have to be, put in before a campaign and then changed over when they run out. So recharging isn't something that we can really do within the scope of this particular instrument setup.
Awesome, thank you. And my second question, and I'll make it quick, is for both, I guess, thinking into the future, what would be the biggest thing that would assist y'all's projects from a USV network group thing? If there was effort that could be pushed in a general direction for all USVs, but also that would benefit y'all's project. And I'll even make a more fun challenge in like 3 sentences or less. What would y'all think?
Liz, do you want to start?
That's a tough one. That's a good one. Next time we do just a webinar series with a round table of that question. Everyone has to answer.
So I feel like I've made some inroads here. I've got a colleague, a collaborator at NASA Ames, Dan Witt, who provided me with some model data at a relatively high resolution. And the idea was to test sailing patterns in a model to check the capabilities of different types of patterns, because it's very expensive to put the drones out there and then be like, we're going to sail a circle today. And then 2 years later, we're going to look at that data and try and understand what it means. So I think it would be great to have a better effort towards like having very conscientious choices of what we're actually sailing with the USVs. And for the types of experiments that a lot of us are doing with this sort of mesoscale spatial magnitudes, that generally means a higher resolution than what's just available online, like free, like, because, and especially in the temporal resolution, the spatial resolutions have been okay generally, but the temporal, if you're wanting to make like an hourly or 2 hourly calculation and your model resolution is daily, it's just really hard to try and get a feel for how that's going to react.
I think I'm going to go for something that this community has said many a time before. That is quality control guidelines. The entire first scientific chapter of my thesis is how do we quality control this? How do we deal with high resolution data? Like what do we actually try and do? And I think it's really, really important to reiterate that, you know, it's not only important on our individual vessels, but we need to be consistent across our vessels.
Great points. Wonderful. Dave, and then we'll go to Paban on the chat. But Dave Velasco, please go ahead.
Hi, yeah. Dave Velasco with Nortec, who's an ADCP manufacturer. Just wanted to make a comment on specifically the Saildrone and the setup over there in terms of the vertical velocities. You might want to just investigate a little bit closer between the timing of the motion correction of the ADCP data, because what they're used on the Saildrone is not motion compensated directly inside of the ADCP itself. And so the timing there difference is important. And so just something for you to investigate into and take a closer look at it, and just don't assume the velocity is going to be okay right off the bat. The timings that are needed, you know, in order for proper motion compensation are in the millisecond range, and it's not being done in the Saildrone. So something to think about.
Okay, I'll have to talk to Dong Jiao, who did some motion correction with the ADCP, but I'm not exactly sure 100% what was done.
It's because
it's a good point. It's super important.
The motion correction, the sensor is actually separate from the ADV. I mean the ADCP in the Saildrone. It's not embedded as part of it, and so the timing of when the velocity is actually sampled and the pulses received back of the transducer is offset from the actual time of the actual sensor is measured. The actual orientation of the sensor. So they claim that they have looked at that. I would just
be wary. Sure. Okay.
Yes. And you might want to actually talk to folks over at APL, since you're at UW, in particular, Andre Schrebin, and he's been doing quite a bit of work with wave-induced biases in surface surface platforms, in particular buoys, and as it compares to ADCP or using ADCP data. And he's got a paper that it's on the works now. Don't think has been published, but you might want to just knock on his door and have a chat with him about that.
Yeah, thanks for that suggestion.
Very good. Thanks for also introducing yourself, Dave. Hopefully everyone else, if you remember, introduce yourself so we get to know this community better. Paban, you had a question. Would you like to say it?
Yeah. Before my question, I think it's 11 o'clock already, but good points from Dave. So we recently submitted a paper on comparison of Saildrone ADCP at 1 kilometer scale, like in a formation at 1 kilometer scale. And we also compared with the ship within 1 kilometer. And we did have a bias of like 1 centimeter per second, but we could not have a conclusion of like whether it is natural variability or just bias from the Saildrone ADCPs. But yeah, my question for Liz is, so I want to know, like, to what depth do you integrate for your vertical velocities, and how much we are missing because the Saildrone ADCP, misses few depths at the surface. So how much we're missing in the dynamics?
So I'm integrating down to about 80 meters is kind of the cutoff. That's how far the ADCP goes to. And then the ADCP itself is the first bin we have with data is around 4.5 meters. So it's fairly close to the surface. But there is some assumption there that that sort of 5-meter bin to the surface is a linear, the velocity in that is linear, right? So we're assuming that the velocity at the surface is 0. Water cannot come out of the surface. And then that next bin at the 5 meters, I'm just assuming it's linear. You could make another assumption, but so that's definitely a location of error. And then you're integrating downwards. So every single error is adding. Yeah.
Thanks.
And Pavan, where are you from and which institute?
I'm from University of Connecticut. I work with Leonel Romero and Cesar Rocha.
Mm-hmm.
Yeah.
Great. Thanks.
I'm a 4th-year PhD student.
Oh, okay. Great. All right. So we are past the hour. We could take one more dying question out there or wrap this up. But anyone want to ask a last question or say something? If you're if you didn't know, the USV Community of Practice paper that Ruth has been charging ahead with is almost ready to be published, which is a very exciting development for the USV community. And I think that's going to be a real treasure chest of information on a whole bunch of aspects when it comes to the community of practice and data and quality control and different sensors and platforms. So look out for that one coming out soon, unless you're already, of course, involved in the work. All right, if there's no other questions, no other hands raised, then I just want to say a big thank you to Liz and Beth for giving us these great presentations and stimulating these questions and discussion. That was really great. And thanks for everyone for joining. We had some 38, 39 people at one stage. It was really great to have the community in this space together. It's great to see you here, a whole mix of researchers and industry and you name it. And look out for the next webinar coming out in maybe 2 months from now or so. We haven't got it planned yet, but look out for the notifications and the adverts for the next one. And if you want to propose any speakers, please let us know. So let's wrap it up there, and thank you very much and have a great day or evening wherever you are. Bye-bye.
Bye-bye.
Thanks, Seb.